This is John Black Super Chemist here to talk about what a mole is. I use moles a lot. I like moles. I don't like talking in grams because equations are used to describe moles or molecules. Not they don't describe grams. But what is a mole? Well, before we get into that, let's talk about what is a dozen. What is a score? A year, a minute, an hour. What are these things? They're numbers. That's all. They're just a number. What's a dozen? 12. What's a mole? It's just the number of molecules. What number is that? 6.021 times 10 to the 23rd. Or, I think they changed it up because when I was young, that's what it was. Now it's 6.022 times 10 to the 23rd. So if I ever use 2-1 here, that's why, because back in the day, that's what we used to call it. So that's how it is. But and you're thinking, well, what good is that? That's a big number, man. How's that going to help me? Well, before I get into that, just because it's kind of interesting, uh, why the we right now we have base our numbers on 10, the Dewey Decimal System, right? And that makes perfect sense. You know what I mean? But back in the day, they used to do things by 12. Their number systems were based on 12 and 60, were two of the well-known numbers, that were based on. Why is that? How do you get 12 and 60? That doesn't make no sense at all. I want you to look at this hand. Look at these hands. It's a terrible drawing, but see the little lines I have on the fingers? Just like on your fingers. You got little lines that go across there. Well, I want you to think about it. If you put your hand out like that, right? Like that, and you took your thumb and you counted each individual section. There's 12 sections. Now, if each time you got to 12 on the other hand, right, you put up a finger. Then you count another 12 on this hand. And you put up another finger. How many fingers are there? 5. 5 times 12 is 60. That's why they base it on 12 and 60. It was easy to count. They had no calculators. That's just a little FYI. All right, so this number, how many moles are how many molecules are in a mole? That is called Avogadro's constant, okay? And it's very, very helpful, okay? I want you to think about something, how this is helpful, okay? Molar masses are how you figure out your equations, right? Now here, let's figure out what H is. Okay, what's the molar mass of H? Now I want you to look here on this periodical chart. It's going to tell you some numbers, right? Look here at boron. It says 10 point whatever, 10.811. Okay, carbon 12.041. I can't see, but it's 12 point something. Look at hydrogen 1.008. That's where you get the molar mass of each element. Okay, and then I'm going to tell you what you do with that molar mass. Okay, H is hydrogen. We're not saying H2. We're saying the element hydrogen, right? It's 1.08. And there's a reason for that, okay? And that's where Avogadro's constant comes in, right? The weight of one nucleon, okay? And a nucleon is either a proton or a neutron. Just an FYI, people call that a Dalton or a, what is it? AMU, atomic mass unit, multiplied by Avogadro's constant equals 1 gram. So that means if I have a proton or a neutron, I hold it in my hand, okay, and then I multiply that by Avogadro's number. So this is how many protons I have in my hand, or neutrons, right? I have them in my hand right here. Protons or neutrons. I got that many in my hand, right? That means I have a gram of protons in my hand, okay? Well, why is H1? Most people think, oh, well, there's one there's one proton, there's one electron, and there's one neutron. First of all, electrons don't get counted. Compared to a proton, electrons are massless. I mean, yes, they have mass, but they're so light, even compared to protons, they're nothing. So they're not even accounted for. All right, and if they are, it doesn't matter. They're so small, it's just unreal. But 90%, and I'm making up numbers here, but 90% of all hydrogen in the universe only has one proton. Okay, it doesn't have any neutrons. Okay, very little hydrogen has a neutron. All right, and when they figure out these molar masses, they're figuring out for the average isotope. Okay, so the average isotope, or the average of all the isotopes together, and since most of them only have one uh, proton and no neutrons, it would be 1. The 0.008 comes from the small percentage of hydrogen that has a neutron. That's what added on. It wasn't the electrons that added this weight on. It was the fact that some of the isotopes are, incorporated into this math, and that's how they figured it out. Now, carbon, it is 12. We know it. It's 6 on the periodical chart. So it has 6 neutrons, 6 protons. That's 12, right? So that would mean 12 grams. It's that simple. All right, the best way to learn this is to do an example, okay? When you see an equation like this, right, you got a base and acid, you're making salt water, right? These equations have numbers. You don't see the 1 because 1 times anything is itself, so you don't put the 1 in. But this means 1 molecule plus 1 molecule yields 1 molecule of this and 1 molecule of that, okay? Now, we as chemists can't use molecules because it's hard to count them. They're very small. So what we use is moles, right? So this also could mean 1 mole of sodium hydroxide plus 1 mole of this yields 1 mole of that and 1 mole of that, okay? You're like, well, how do I know how much a mole is? Well, we just figured that out, right? We go to the periodical chart, we look up sodium, we look up oxygen, and we look up hydrogen. 23, 16, and 1. We add them together. It gives us 40. That means 1 mole of sodium hydroxide is 40 grams. So if we're going to do this all in moles, we would add 40 grams of this. How much of the HCl? It's a liquid. And it has water in it. It's confusing. What I do with this is minus 32%. I get it at Lowe's. That means it's 10 molar, which makes it nice and simple. 10 molar means that in a liter of solution, you have 10 moles of HCl. A liter of hydrochloric acid, you have 10 moles of HCl. So that's easy to figure out, right? If 10 moles are in 1,000 milliliters, or 1 liter, then 1 mole is in 1/10 of this, which is 100 milliliters. So you'd add 100 milliliters of HCl, 40 grams of sodium hydroxide, and there you go. Do your reaction. If let's say you wanted to do more, you wanted to do less. You're like, well, what if I don't want to do an exact mole? Well, okay, fine. Let's say you do half of 40 grams and you do 20 grams. Well, then you do half of this. Instead of 100 milliliters, put in 50 milliliters. Put in 5 times this, put in 5 times that. Whatever you multiply or divide this by, you have to multiply or divide the same exact amount on all these other stuff. There's only 2 here, but you know what I'm saying? If there was more, you'd have to do it to every last one of them so that they would all be 10% or they would all be 5 times. And keep in mind when you're making a molar solution, like let's say you want to make a solution of 4 molar sodium hydroxide. You don't take a liter of water and throw in your sodium hydroxide because then your solution will be more than a liter. What you do is you take a half a liter, dissolve your sodium hydroxide in it. Then after it dissolves, you fill in more water so that it adds up to a liter. Okay? Otherwise, you'll have more than a liter and you won't have your exact molarity. That's called molarity. You say, what's the molarity of 32% hydrochloric acid? It's 10 molar. Let's do another example. We got calcium chloride plus sodium sulfate yields calcium sulfate and sodium chloride. Now, this is the same type of thing as doing hydroxides. Calcium sulfate is insoluble, okay? Just like most transition metal hydroxides. So I put in sodium sulfate and I put in calcium chloride. They all dissolve, right? But when a calcium ion meets a sulfate ion, it precipitates out, okay? And then you can filter it out, okay? You can just go to Wikipedia, type in calcium chloride, and it will give you the molar mass. You know what I mean? Same with this. Just type it in, gives you the molar mass. But here I'm going to give you a little trip up, okay? This that we have we figured out if it was anhydrous, but what if it's a decahydrate where water molecules are incorporated into the crystal lattice? A decahydrate has 10 hydrates, right? Well, then you'd have to figure that out, right? So HHO, that's 18 grams per mole for water. You have 10 of them, right? For every molecule of this, you got 10 of these. So that means you multiply that by 10, that's 180. Now you take this for the weight of that, and you take this for the weight of the water, and you add them together, see? So now it's 322 grams per mole. So if you did this reaction and you had this, and it wasn't anhydrous, it has the decahydrate, you'd need 110 or 111 grams of this, and then you'd need 322 grams of the sodium sulfate, not 142, because 180 grams of that would be water. So you have to take that into consideration. You know, if you have any hydrates, always remember, especially if it's a decahydrate, that's a lot of weight. This example, I chose it because it's a liquid. Here's my thing. I'm oxidizing alcohol with sulfuric acid and dichromate to make formaldehyde. Okay. Now here's a secret to the you know, instead of figuring out how many carbons, and there's 12 for that, and there's oxygen, that's 16, and adding everything up to get your molar mass, you can just go to Wikipedia, type in ethanol, and look to the right. It'll have a picture of ethanol and a bunch of statistics or properties. Scroll down and you'll see molar mass, and it'll tell you what it is. Same with sulfuric acid. Just type in sulfuric acid, scroll down, you know, where all the little properties are, and you'll see it says 98 grams per mole. Now, two things below that is the density. You would write that down too. And the reason why is, I mean, you could just weigh this stuff up. You don't have to do this if you don't want to. I prefer to weigh, I don't like to weigh liquids up. I like to measure them. So what I do is I take the molar mass divided by the density. You can see I just put it right down here. That tells me how many, because this is grams per mole. And I'll cancel out the grams and put milliliters in there, right? Cancel the grams off. It'll be milliliter per mole. Now I know I need 58 milliliters per mole of ethanol. Now I do the same thing here. I divide the molar mass by the density. I get 53 milliliters per mole, but this is different. That's why I chose this. Sulfuric acid has 2% water, right? So I take this and I divide by 0.98. Now if I had 90% sulfuric acid, I'd divide by 0.9. If I had 92%, I'd divide by 0.92. If I had 40%, I'd divide by 0.4, etc. That gives me how many 54.4 milliliters of sulfuric acid would be equivalent to 1 mole. All right, so we already figured out it was 58 milliliters for a mole of ethanol. We need 3 moles, though. That's why I chose this example. So you multiply that by 3, you get 174 milliliters. Figured out it was 54 milliliters for the sulfuric acid, but you need 4 moles. So 4 times that is 217 milliliters. We looked this up on Wikipedia. It's 294 grams per mole. So these are the ratios you need. You might ask, well, what if you don't want to use this much? What if you want to use less or more? Well, let's say you want to use 10%. Use 17.4 grams here. That means you use 10% of this and 10% of that. It's that simple. If you use twice as much, you use twice as much as this and twice as much as that. Okay. Now, I want you to keep in mind, just because it says stoichiometrically to do this, that doesn't mean that that's the way you do it. Okay, there are some, you know, like if you have a gas, you have to take into consideration that there's air in your apparatus that you need to push out first. And when you're done with your reaction, you know, that vessel will be filled up with your gas. It won't be reactive. It'll be replacing the air that was in there. So you have to take that into account, and also gas escapes. You know, you bubble it through a liquid, and some of it doesn't react, and it goes back into the atmosphere. So you have to take into consideration that. Acids, you know, as a reaction goes forward, unless it's a catalytic thing, as it goes forward, your acid gets more dilute. So by the time you're done, you know, down to the last 10% of your reaction, you might not have enough acid in there to actually do the reaction. So you might have to put extra in for that. You have to think of that ahead of time when you're doing your stoichiometry.